Okay, I think we can start today's session. So we are very happy to have Cristina Mondino tell us about astrometric weak lensing. Oh, and by the way, of course we moved the talks now. There's at 5. There's the microboon thing. If anyone is interested in watching it here, to tell us, and then we can probably do it.
Okay,
yeah.
can start?
Yes.
Okay, thank you very much. So during this talk, I'm gonna describe some techniques that aim at probing dark matter clumpiness on subgalactic scales. And these techniques rely uniquely on the gravitational lensing effect that the dark matter clumps can have on background luminous sources. Can you hear me? Okay. Yeah, as I was saying, we will be looking for gravitational lensing effects that the dark matter substructure induce on background luminous sources, and in particular on the apparent motion that they induce in these background stars. And the talk is based on the work that I started back at NYU with Anna Maria, Ken, and Neil, and that we published last year, but also I'm going to present some of ongoing work that I'm doing with the same group of people plus an undergrad at NYU, Andreas. Okay, so since our main goal is to probe dark matter substructures, let me start by reminding you where this dark matter structure come from. And as you all know, our best model for describing the evolution and history of our universe is the standard cosmological model, or lambda CDM. And within this framework, we know that early on, the universe was almost perfectly homogeneous, up to tiny fluctuations of 1 part in 10 to the 5 that we see, for example, in the temperature of the CMB photons. And these hotter and colder spots also correspond to overdensities and underdensity in the matter power spectrum. And then when the universe becomes matter dominated, the denser spot will start growing and form all the visible structures that we see in our universe today. So indeed, our universe is very far from homogeneous today. We have a variety of hierarchy of structures of different masses and length scales, from galaxy clusters down to galaxies and structures within galaxies themselves, like dwarf galaxies or satellite galaxies and globular clusters. And we can test this prediction of lambda CDM very well down to length scale of the order of megaparsec or so. But as we try to go to smaller scales and lighter structures, then observing them directly becomes challenging, because the smallest and lighter structures have a weaker gravitational potential, and they are not expected to have had supported enough star formation for them to have enough stars to be seen directly. And also testing them indirectly through gravitational lensing is challenging, because these are extended fluffy objects, and so they don't have a steep, their gravitational potential is not very steep, and typically gravitational lensing effects are suppressed by their finite size. So, however, even though testing lambda CDM down to subgalactic scales is challenging, there are, sorry, I want to remove the, okay, never mind. Never mind.
Is it the
Wait.
Here, yeah. No,
Is
yeah. Try to move it from here. Yes.
okay. Okay. Sorry. Okay, I can keep going maybe in the meantime. So I was saying there are also theoretically motivated scenarios that predict. Okay, it doesn't matter if you. I will just keep going. So there are some theoretically motivated scenarios that predict deviations from lambda CDM at subgalactic scales, which are still compatible with current observations, and that lead to the formation of more compact structures on the smallest scales. And these generically can arise in two cases. For example, if we modify the standard cosmological evolution and we have a period of early matter domination, or for example, if we have a dark sector which is richer than a single cold dark matter component, and we have, for example, a bosonic field with self-interaction or a fermionic field with dissipative interaction that will bring to the formation of dark stars. And there has been significant exploration of these scenarios recently, and there is still a lot of work that needs to be done, but this is not going to be the focus of my talk. I just wanted to point out that we can have compact structures, more compact than what we expect in lambda CDM on the smallest scales. And it's interesting to test them, to test these scenarios with observations. And there are several methods that people have been using to look for dark matter substructures on subgalactic scales. Some of these also rely on gravitational lensing. For example, by looking for features in strong extragalactic lenses, or techniques have been suggested to look for time delays in pulsar timing observations. And then there is another category of techniques that instead wants to look for the direct gravitational effect of dark matter clumps within the Milky Way, for example, on stellar streams or the phase space distribution of halo stars. So our method is complementary to all these methods that have been suggested, and it's part of this wide program to probe dark matter structures on the smallest scales. Okay, so let me get to our technique, and starting by describing the physical effect. So this is the plan of the talk. First, I'm going to describe our physical effect and the observables that we define to look for them. In the second part, I'm going to describe the data set and present results from an analysis using the velocity of stars measured by Gaia. And then finally, I'm going to present future projections and also, time permitting, mention a couple of other lensing observables that are not related to dark matter structures. Okay, so astrometric weak lensing, what does it mean? Astrometric refers to the fact that we are looking at the effect of the angular deflection of the light centroid of the background star, and not at the effect of light magnification, like in photometric lensing, for example. And then we are in the weak lensing regime, meaning that the impact parameter is such that the observer only resolves one image for the background source. So in this regime, what happens is that the observer will see the background sources deflected by a two-dimensional angular shift, which is parametrically given by this formula. So it's proportional to the lens mass enclosed within the impact parameter and inversely proportional to the impact parameter, which I'm denoting here by B. And it's just the distance of the closest approach between the light ray and the center of the lens. And if we plug in some numbers for a typical dark matter subhalo, we get that the angular deflection is of the order of few milliarc second. But if we try to look for this effect directly in the static regime, and we take a field of stars which are randomly distributed on the sky, we imagine that there is a lens between us and the stars. What happens is that all the stars will be deflected radially away from the center of the lens. But in practice, if we're looking for a dark lens, we don't know where it is, and we also don't know where the original position of the stars were. So the presence of the lens does induce some underdensity in the field of stars, but these are smaller than the stochastic fluctuations. So we need to take a step forward by going into the time domain. Now, if we look at the same field of stars for a finite amount of time, and during this observational time, the lens moves with respect to the observer, what happens is that the relative impact parameter between the stars and the lens will change over time, and so will the angular deflection. And so as the lens goes through the field of stars, it will appear as if the stars are moving. So if we measure the velocities of all these stars, we will notice that they distribute themselves according to a specific pattern, which is a dipole profile. And indeed, you can see how the dipole profile arises if we take again the angular deflection expression I wrote before. And now we have an impact parameter that changes over time. This can happen, for example, if the lens has a linear motion with some velocity v. And then let me first work in the regime where the change in impact parameter, the relative change in impact parameter is small over the observational time. And in most of the talk, I'm just going to be in this regime. And in this case, we can just expand here around the small delta B over B. And the leading order effect that we get is a leading order in VL times T. So it's an induced angular velocity, delta mu, which is the time derivative of a monopole profile. And so it's going to be a dipole profile. There is a correction to this dipole, which is due to the fact that, which is coming from the spatial derivative of the lens mass. And I'm not showing it here for simplicity, but we can, of course, include it. And then there is an next to leading order effect at order VL times T squared, which is going to be an induced angular acceleration. And it's going to have a quadruple profile.
So the only velocity that matters is the one in the lens plane?
Yeah, it's the relative velocity between the lens and the observer and the background stars.
Okay, because, okay, the stars are so far that you
yeah,
don't...
exactly. So there is also a term which is velocity of the stars, but it's multiplied by distance of the lens over distance of the stars. And yeah, you cannot read it there, but there is also a nonlinear motion that the lens can have. So remember, when we look at anything on the sky, we're always looking at it by going around the solar system. And so we have where there is an induced circular motion, which is the parallax motion. And so if the lens would have this parallax motion and can also, as a consequence, induce an anomalous parallax in the background stars. Any more questions? Okay, so the magnitude of the induced angular velocity is very small, is sub-microsecond per year. So it's impossible to see it for one individual star, but we can add up the effect from multiple stars. And we do so by defining these template observables. So again, remember, we are always in this regime. Here I'm showing the expected lens-induced velocity, acceleration, and parallax. The magnitude depends on a combination of this combination of lens parameters. And then the profile, I'm representing it here in this density plot for the two components, horizontal and vertical component of the angular velocity. And this depends on two properties of the lens. One is the characteristic angular size, which is the radius of this white blob here. And the other one is the direction of the velocity of the lens, that here I chose to be horizontal. And here, just for simplicity, I'm not showing, I'm assuming that all the lens mass is included within this characteristic angular size, so that outside is a perfect dipole. But then if we include the other term, which is the derivative, the spatial derivative of the lens mass, we have a profile which depends on the radial mass density profile. And so this template would capture order 1 of the signal, but then the signal will be maximized, of course, if our matched filter here matches the correct one with the correct lens mass profile. And it's very slightly, for example, if we have an NFW profile or a Gaussian profile of the lens. So once we have this induced velocity, we define the template test statistic, this quantity tau, as the sum over all the stars in around the lens of the dot product between the observed stellar velocity and the expected velocity profile, this match filter, using inverse variance squared as weight for each star. And this quantity is maximized this quantity is maximized when the observed stellar velocities match the matched filter, while it should average to 0 if they are just Gaussianly distributed with a 0 mean. We can do the same thing for accelerations and parallax, and then estimate the signal to noise ratio by computing the average tau for signal over the variance of tau for noise. And you see that we get some dependence on the stellar properties. In particular, it goes like the square root of the angular number density of background stars over the effective dispersion in the velocity of the stars. And then it depends on the lens parameters. This is for an individual lens. And then if we have a population of lenses, the signal to noise ratio will be maximized by the lens which has the smallest distance, so the one that is closer to us, and the one that is more compact with the smallest physical size. And I'm going to use this later on to show sensitivity projections by taking the maximum signal to noise ratio. Let me now move on to describing the data set. So the data set we're using for our analysis is available thanks to the Gaia mission, which is currently the Gaia satellite is measuring velocities and position for billion of stars in the Milky Way and in the surrounding. And they currently release data for 2 and 3 years of observations. And they are planning to operate for a total of 10 years. So what Gaia sees, this Gaia satellite continuously rotates around the axis, and it's scanning the sky multiple times. So what they see for each individual, they see each individual source multiple times, and then they perform a fit through these individual observations. So this is what they would see for a star which is moving with a velocity and a non-zero parallax. And they perform this 5-parameter fit that is then provided to us. For now, they are not including angular accelerations because most of the stars are not expected to have an acceleration. But eventually, they should release all the individual time series of the observations. So we could, in principle, fit for an angular acceleration. And they might also do it themselves. But what we can do for now is the velocity template, look for the velocity templates. And so for that, we have to choose the best stellar target by maximizing the figure of merit that appears in the signal to noise ratio. That happens to be maximized for stars which are far away, so they have a small intrinsic velocity dispersion, but they still need to be dense objects. So the best target are the Magellanic Clouds, these luminous sources in the south hemisphere. So we take the stars in the Magellanic Clouds, and then we zoom in into particular location, we take the observed velocities, and we compute the dot product with our match filter. And we repeat this for different template locations, so by scanning over the sky, and by varying also the angular size, characteristic angular size, and for the two template orientations, horizontal and vertical. So the result is that we end up with a number of computed tau values on the data. Here I'm showing the histograms for tau for template in the horizontal and vertical directions for a bunch of different angular sizes. And you see that these distributions are picked around 0, and they have roughly a Gaussian distribution, which is what you would expect for noise. While for signal, we would expect some large value of tau here in the tails. So given this is what we see in the data, we then proceeded to set some constraints on the presence of lenses in front of the Magellanic Clouds. So we take a population of lenses with a given mass, physical size, and fractional abundance with respect to the dark matter abundance. And then we perform some simulations where we include data-driven noise and then a signal coming from the population of lenses. And then we compute the test statistic for all the simulations. And if we see that 90% of the times we get a larger value than the one observed in the data, then we conclude that point is excluded. And this is the result that we get by doing the analysis on Gaia data release 2, which corresponds to approximately 2 years of observation. Fractional abundance of compact lenses as a function of mass for a few different physical sizes. So as you might notice here, we're not yet sensitive to subfraction of dark matter in the form of compact lenses. But so you might think that this is a limit in a non-physical region of the parameter space. But in reality, there are two caveats. The first one is that we're looking at substructures in front of the Magellanic Clouds. And it has been shown that the Magellanic Clouds themselves have, both in simulations and data, they have a non-negligible effect on the Milky Way halo. And so it's not totally crazy to think that there might be more substructures in that direction. But also, more importantly, this is an analysis that we did with a partial data release. And we expect it to improve considerably over time because most of the stars in the Magellanic Clouds are very faint. And so their observed velocity dispersion is still statistically limited.
But you can have overdensities that are rare, and then the omega would be bigger than dark matter, no?
They would be, sorry?
I mean, if you're looking at something, at some very rare substructure that somehow arrived in your view, then that can have a density higher, no, than the density of the dark matter.
Yeah, the density of the clump, yeah, is much higher. But what I'm showing, the fractional abundance here is with respect to the total dark matter density in the Milky Way halo.
Oh, I see. I see. Okay, I think
so. Yeah, it's you have more dark matter in that direction. That's what I'm saying. But yeah, in the location of the lens, you have a very large overdensity, of course. So the observations for stars in the Magellanic Clouds, the proper motion dispersion is expected to improve by an order of magnitude or more. And we already got an improvement by running the analysis on the data that were released later last year that correspond to almost 3 years of observations. But let me now show you the most optimistic projections for the end of the mission for both the velocity and the acceleration templates. So the blue curve here represents a signal to noise ratio equal to 1 for the velocity template analysis on the LMC. Again, I'm showing subhalo fraction as a function of subhalo mass in unit of solar masses. And the same thing for the acceleration template. In the case of the acceleration, we don't need to look for stars in the Magellanic Clouds because also Milky Way stars are not expected to have an acceleration. And so the acceleration dispersion is expected to be very small for all the stars observed by Gaia. So we can use all the stars in the disk covering a larger solid angle on the sky and being sensitive to lighter lenses. And in particular, this is interesting also because we could potentially be sensitive to astrophysical black holes, for example. They have solar mass, 10 solar masses or so. But yeah, of course, for now, we don't have angular accelerations. We would like to get them from the 7-parameter fit. And in the meantime, for that, we need to wait. But in the meantime, what we're trying to do is that we're trying to hack the acceleration from what we currently have. So if you perform a 5-parameter fit of a star that also is moving with some acceleration over a different time of observation, you would expect to get a different result for the 2 fit over a different observational time. And so by using the best fit from Gaia DR2 and early data release 3, in principle, we should see an offset in the position of the same source, which is proportional to the angular acceleration. So we're trying to build a catalog of these hacked accelerations. And yeah, finally, I think I have some time to mention these other application of astrometric weak lensing, which are not as interesting for fundamental physics, but they are still nice application in my point of view. So one thing that we tried to look for was star-star lensing. So your lens doesn't need to be a dark object, but if you have one foreground massive star that happens to be accidentally close to a background star, then the foreground star itself can serve as a lens. And we found millions of such accidental pairs in the Gaia catalog. Of course, there is a limit on how close these 2 accidental pairs can be. because Gaia cannot resolve arbitrarily closed sources. Yeah, unfortunately, we found that for stars that are a solar mass or so, the lensing signal, the signal to noise ratio for the velocity template and also the other two, acceleration and parallax, is just below 1. So we cannot see the signal in the current data, but potentially we can do that in the future. And finally, there are another type of lens that we can look for. This is on our to-do list, is potential planet 9, which the existence of which has been postulated because of the clustering of orbits in the outer solar system. And there are surveys that are currently looking for planet 9, for example, by the radiation which is emitted directly by the planet or reflected by the planet. But both of these techniques are not very sensitive in crowded regions if there are background sources. So if the planet happens to be in one of these spots, then it could potentially induce gravitational lensing in the background sources. And in this case, we need to be in the opposite regime of a very close approach where the planet moves, covers a large portion of the sky during the observational time. And then it would induce a blip in the position of the star. And so essentially, these stars that fall behind the planet would not be well described by the 5-parameter fit that Gaia is performing. And so they would appear to have a bad chi-square for the fit. So we can define a template for the chi-square and in principle look for such pattern on the sky as a function of the planet position and the planet trajectory. So yeah, I can conclude here. I hope I convince you that astrometric weak lensing is an exciting place to probe dark matter subhalos and also other type of lenses. And I'm happy to take any questions or explain any of this better. Thanks.
Thank you. Questions?
Yeah, thanks for this nice talk. I think that's really exciting. So you mentioned that you looked at templates for different halo profiles. How does the sensitivity depend on the halo profile, and how well will you be able to distinguish between different halo profiles?
Right. So in practice, in our analysis, we just picked one profile, which was an NFW profile, which we truncated with a Gaussian.
Yeah, fair enough.
Because we didn't see any signal. And so, yeah, we didn't try to, well, we did try different templates earlier on, and then we just picked one for the final results. But any template that you use should capture order 1 of the signal.
The reason I'm asking is because towards the end, you mentioned the possibility that in the future, you might be able to see stellar mass black holes with this. And that would, of course, be like one of the extreme cases for the template profile. So can I assume that by order of magnitude, the order of magnitude of the sensitivity will remain the same for an NFW subhalo and a really compact object, or should I expect a large change there?
Right. So there is a minimum physical size below which you cannot distinguish between an extended lens and a point light, which depends just on the angular number density of stars. So if your physical size is smaller than the typical separation between two stars, you cannot distinguish between a point light. Yeah. So yeah, and a black hole would just appear to be one of these.
May I also ask a more technical question? So I understood how you define your how should I say, your test statistics, but I didn't quite get how you account for the chance probability that the proper motion of the stars just happens to align in this dipole pattern by chance. So how do I get from this test statistic that is, for instance, this mu dot mu tilde divided by sigma square? How do I get from there to the actual limit?
Yeah, I skipped a lot of details. So now we actually set the limit, but we don't know. Because we cannot trust that the velocity dispersion is exactly Gaussian. So that's why we use the simulations in which we inject some noise, which is modeled from the data themselves. So if we knew that the noise was exactly Gaussian, then we could just compute the test statistic and compute a probability.
But you're taking the noise from the data and injecting that into the simulation.
Yeah, exactly.
Okay.
For stars with different magnitude, we inject a different noise.
All right, that answers it. Thanks.
Thanks.
This is a naive question. Is there any population of stars for which we have now many decades of astrometric data, and you could hope to do a, not the whole statistical, but just look for individual stars' motion over a century or something?
Yeah, so there are catalogs of the entire sky, but they don't have good enough astrometric precision. And then there are other observations, for example, from Hubble, which have extremely good astrometric precision, and they are just much smaller field of views. And we were trying to use some of those, but we found that, some astrophysicists told us that there were different observations of the Andromeda galaxy, I think, from Hubble at different times, which were like 10 years apart. But then we needed more help in combining them to actually get the velocity of the stars. And we just never got there. But in principle, we're also interested in doing that.
Thank you.
Any more questions?
Thanks for the nice talk. I wanted to ask something about this exclusion plot that you showed at the end with projections.
Yeah.
So can you please remind me, what is the expected signal in this plot for lambda CDM and WIMP, for instance, from simulations? How many substructures do we expect?
Yeah. Okay, so here is just, so the lens mass, the subfraction of dark matter in the form of compact lenses versus mass. What I'm not showing here is what's the physical size of these lenses, because I'm taking the maximum signal to noise ratio, which happens for the most compact lenses. So for example, if we take a lens of 10 to the 5 solar masses, the physical size would be of sub-parsec, like 0.1 parsec. So it would be a very compact object. And then, with an abundance with respect to the dark matter abundance, which is given by, you can read on the y-axis.
No, but I was just wondering, for example, if I run an n-body simulation,
Ah.
what do I expect? What is the signal that I should see? If you know it.
No, here I'm just assuming that the lenses are distributed. That we have lenses with a given abundance in the Milky Way, but I'm not. I'm not saying how these lenses would happen to be there. You're right. In principle, you should do a full.
Well, I didn't mean in putting the exclusion plots. I was just wondering what would be the signal that we expect.
That depends on. It depends on your model, right? And To have a signal, you would need to have such compact lenses with that mass. But yeah.
All right.
Right. So the question was if there are future prospects with respect to Gaia. So within Gaia itself, there are future prospects because we're just we now only have access to partial measurements, not for the total end of the mission. Other astrometric survey which are already founded, yeah, I'm not aware of. But well, in the future, there are other survey like SKA, which should measure, for example, a very good astrometry for quasars over the entire sky. So that's one interesting future prospect. But yeah, also just within Gaia, we can improve.
Okay, if there are no further questions, we can thank Cristina again.